So my third and probably last topic is about image recognition, which is how in that first example did we reject the cat and learn all the other, figure out where all the other images were on the sky. So the paper we wrote, so the project that I'm going to tell you about is called astrometry.net. And the first author is Dustin Lang, who was on my first view graph as well. The idea behind this project was, well, we had various ideas behind it. One way of thinking about it is as a computer vision project, where you say, this is an image, what's in an image of? I was actually, and Sam and Dustin were interested in it from that perspective. I was actually interested in it from a very different perspective. I was interested in it from the perspective of, I have astronomical data that's corrupted, and I want to uncorrupt it. So I want to be able to take the images that we have where we've lost the information. So for instance, a good example is the Harvard plate archive. So at Harvard University, there's an enormous room with shelves and shelves of glass plates where images that are images that were taken with telescopes. In fact, glass plates were used up into the 80s because CCDs only came in the 80s, and so people were developing these glass plates. And so there's this library, and that library of glass plates contains an image. The average coverage of the sky is 500 times, meaning if you could assemble all the data that's in there, you would get an image of the sky 500 times over the last over the years from something like 1870 to 1985. So that's a pretty valuable and powerful resource. The problem is, for each plate is in a paper envelope on which the observer wrote the coordinates, and 10% of the time those coordinates are wrong. So we were like, how are we going to use these data? And that was sort of the astronomical motivation. And but then when we brought this to Sam's group, he was like, ooh, that's a fun computer vision problem. Now, the paper for this is dated 2009. We actually were on the web by about 2005. So I believe that we're the first really functional, high fidelity, low false positive rate, precise image recognition system of any kind. Now there's all sorts of non-text search out there. You can hold up your phone at the speaker and it tells you what song's playing, and you can take a picture of a leaf and it tells you what tree it is. So now this seems all perfectly normal. But if you wind the clock back to 2005, we really were ahead of the game, and I'm very proud of that, as you can tell. The one problem is that this question is a very, answering this question in general, obviously there's people in this room who would like to have the answer to that question in general, and it's like a $1 trillion industry. And one mistake we made is that we did solve this problem, but we solved it in the one domain where I can see no commercial value whatsoever, which is astronomy. But anyway, the idea is, so the way I think of this is as a calibration problem, but other people would think of it as a recognition problem. Now, the reason I'm going to tell you about this is partly that I'm very proud of it, but partly because you'll see that there's a lot of different ideas from machine learning that came in, and there's a lot of new things we could do if we went further with this. And of course, everything in here is open. The code's all open source, and the data are all freely available. By the way, we run in Flickr. Oh yeah, I should just show you that just because I can. The web is not really working right now. However, I preloaded some pages during Zubin's talk. These took entirety of Zubin's talk to load. You can't see these images because it's too dark. But this is on Flickr. I just searched for the word astrometry. If you search for the word astronomy, you get lots of crap. Now, astrometry, the reason I searched for this is we run a little group on Flickr. So if you roll down here, you can see there's a lot of these images you can't really see. They're images of the night sky. And then this is an image of a textbook about astrometry. But anyway, the other ones are images of the night sky. Mainly, I have no idea what that is. But anyway, I took these images. I clicked on one of them. Here's one of the ones. And this one is tagged astrometry because it's been added here to the group called astrometry. Okay? This sounds like an ad for Flickr, but it's not. I have no interest in Flickr. In fact, it's about to go bankrupt. You can buy Flickr if you want it. But anyway, because it's one of the Yahoo companies, so it's going down right now. But anyway, when you add your image to the group astrometry, a few seconds later, this happens. Hello, this is the blind astrometry solver. Your results are blah, 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 and it tells you a bunch of technical information about your image. And that is our code running the Flickr API. So we're trolling Flickr for images that get added to the pool, and when they get added to the pool, we come in and we tag them. And the most amusing thing is we do this, you see? Look, there's the California Nebula. See, there's the California Nebula. The funny thing is I didn't choose the image to have that in it, but it happens to have it in it. And astrometry.net has very helpfully tagged the California Nebula in the image. Okay, good. I just wanted to show that off. That's one of the things that's really was fun about working with Sam, and we've tried to preserve in our work, is that when we have something that works, we put it on the web, so anybody can play with it. And I'll give you a URL in a minute if you want to play with, if you want to actually submit some images. In fact, when Sam used to give talks about this, he would ask people to take a picture of the night sky the night before and bring it to the talk so that he could show that it worked. Good, and the astrometry.net has processed millions of things, so it involves some incredibly trivial computer vision doing source detection, then some amusing data structures things where we do geometric hashing, and then we're going to do lookup. We do geometric hashing of constellations of stars, and then do very fast lookup. And for some applications, we have the fastest KD tree in the world. And then the decision making we have to decide when an image comes in whether we're going to say to the person who submitted it, yes, we found a solution, or we haven't. And of course, we're probabilistic reasoners, so we only have probabilities. So to turn the probabilities into a decision, we actually have an explicit utility model, and we're trying to optimize our long-term future discounted free cash flow. That's our goal. Which, by the way, should be everybody's goal. Probabilistic reasoning only gives you probabilities, and in your life, you have to make decisions. Like, should I marry this person? And you should be thinking about your long-term future discounted free cash flow under the assumption that everything is fungible to dollars, at least marginally. See what I'm saying? So that at least that you can make marginal decisions on the basis of dollars. Like for an extra $300, I would spend an extra evening with my kids. Then if you're willing to make those kinds of decisions, then, actually, I said that with the wrong sign. It sounded really bad, didn't it? But anyway, this is something I learned at Google. I was at Google for like a month, and the only thing I learned at Google was that you should be optimizing your long-term future discounted free cash flow. The problem with it is this really is true. This is, Zubin mentioned at the end of his talk about computational resources. You have to decide, have I sampled enough to make my predictions? And sampling costs something, and having bad predictions costs something. So you have to be able to trade them off. How can you trade off sampling versus predictions? They're measured in different units. You have to convert them to the same units. What are those units? Dollars. Dollars in what? Long-term future discounted free cash flow. You have to say, how much does it cost me to do this computation? How much does it cost me to delay my publication? And how much do I get for having performance? So in some sense, I think everything should be done this way. The problem is it's very hard to take this engineering view about every aspect of your life. It gets confusing to think about, whether delaying a publication by a week is the same as having 0.2 bits better prediction. I don't know. It depends on a lot of things. But anyway, so one of the things I like about optimizing this is it's impossible. It's literally impossible. It's Sisyphus kind of thing. It's like achieving happiness or inner peace. It's impossible to optimize this, but it's nonetheless the thing we must all do. So, but the reason it's impossible is that you never understand your customers, and your customers are changing all the time. like if you think of this from the point of view of a business. So for astrometry.net, we really do think of it as a business. We have customers who are astronomers bringing us images. We're trying to deliver to them correct metadata. And because we're promising that the metadata we're producing is correct, our utility is very skewed. Giving people back a false positive is very, very bad for our business. So that's one of the reasons we went to thinking about this in terms of utility, because we wanted to understand our customers. Yes?
What is long-term discounted free cash flow?
Oh, good. Long-term means you're looking to the timescales over which there can be qualitative changes in your operations. So like longer than years. So future would be in there. Discounted means you're applying your personal discount rate, like interest rate. So you'd rather have $100 now than $100 in 10 years by some quite large discount rate, right? And then free cash flow is different from profit, because profit is the thing you spend. Profit is what you get after you've spent cash on capital improvements. So you could say profit there, but the reason profit would be wrong is you might build like a summer home. You might do so well that you build a summer home, and that improves your happiness. But the fact that you could build the summer home should be counted in your utility. That should be counted as something you're trying to optimize. You're trying to optimize the number of summer homes you have. So that should be in there, so you don't want to remove it as profit. So that's why it's cash flow, free cash flow, not profit. Does that make sense? Do you disagree?
I have to think about it.
I think, I seriously, everyone thinks I'm joking when I first bring it up. I'm not joking. I actually think this is what you should be optimizing. You know, people talk about model choice, and Bayesians often say, oh, you have to compute the evidence to decide between one model and another, this marginalized likelihood. Well, that's fine. You can compute that all you like, but then you have to multiply by your utility before you make the decision. You can't just take the more probable model. The more probable model might take a year to compute, and the less probable model might take a millisecond to compute. And then you're not going to want to choose the more probable model in most cases. Okay, good. So let's do some demos. Let's play with this a little bit. So here is an image. Anybody want to say what it's an image of?
Pleiades.
The Pleiades. Somebody was saying stars, and Bernard said the Pleiades. Both answers are correct. There's another answer that's correct, which is nebula, because you see the Pleiades is young stars, and there's a gaseous nebula there that the stars are forming in. It's a very interesting and beautiful system. Although it's called the Seven Sisters, and I don't know what seven they're talking about, but anyway. And then you run it through astrometry.net, and we return you information like this. And this is the sense in which it is an image recognition system. You gave me an image. I told you what it's an image of. And there it is. So I have succeeded. So that's image recognition. Now, how does it work under the hood? I'm going to tell you a little bit about how it works. But in this particular case, there's this funny chevron-shaped thing here. That green thing is a quadrangle. It's a set of 4 stars. And that set of 4 stars was a key that appeared in the image and also appeared in a database of pre-computed quads that we had pre-computed before the show. It found the match. Then, based on that match, it asked, can I explain the other stars in the image? Okay, so here, in this situation, the red stars, got it. So can you see there are red circles? Not everyone can probably see the red circles. Anyway, there are red circles on this image which are circling the objects in this image that our software believes are stars. So our software is total crap for a lot of reasons. One of the reasons is it has to be fast, because we need to do this really, really fast. So we don't do anything very sophisticated to figure out what the stars are. We do something very unsophisticated to find points of light. And those are circled in red. And then stars that are indexed in our indexing system, and our indexing system is extremely complicated, but this is one layer of the indexing system, are marked in green. Okay? And the match that we got for this quadrangle makes a prediction. Once you match that quadrangle, that implies, oh, this image must be here at this orientation and with this scale. And then you can ask, in that image, are there other green stars that are well matched by red stars? And you can see there are. See, this green star here has a red circle around it. This green star does. This one does. These two don't. So not all of them are well explained, but many of them are well explained. And then there's an additional issue, which is that there's lots of red stars here that don't have a green circle. So the question is, probabilistically speaking, did we make a good match here? Are we right? Is this match a good match? Like, if you look at it, are you convinced that the red stars and the green stars are a good match?
Depends how big your database of green stars is.
It does. So good. So that's one of the reasons. But so good. So there's one question is, how much did we search to find this? Because the database of green stars might just go on and on and on. Now, this image is a few degrees on a side. So there's only about 10, it's actually more like 10 degrees on a side. So there's only something like 400 patches of the sky this large. And there's the density of green stars. So you can see that, in fact, there's only about 400 shots at this, say. Now, are you convinced that it's a good match? It's an interesting question to ask, because an astronomer is absolutely convinced by this 100%. I mean, even if only 2 other stars had matched, an astronomer would be like, yeah, hell yeah, that's correct. Because the chance of 2 of those circles being concentric is very low. Like, there aren't any green-red circles that are nearly concentric. They're all either exactly concentric or not on at all. You see how that, it's very clear which stars match. So to an astronomer, hell, oh yeah. And in fact, if you take our probabilistic, we of course have a probabilistic model for this process. We ask, what's the probability that you would get this many matches by chance, you know, versus a random patch of sky? And this would have some unmentionable probability, like e to the hundreds in that. Because it's very precise. That's a very, very precise match. This is absolutely no doubt about that.
Will you pick the 4 to start off with?
Good. I'll say a little bit about that. Hopefully I will say enough about it. But if I don't, ask me that again. Because the question is all about these quads. And in fact, when we solved this image, for instance, in fact, this is about the 100,000th match it worked on. So what happens is it matches many quadrangles, but almost every quadrangle it matches is a match by chance, and then the other stars don't match up, don't align at all. So it tries hundreds of shots, and then bam, it gets it. Or thousands, or hundreds of thousands, or millions in some cases. It often takes a long time. One of the really interesting things is we have to get lucky to work fast. Okay, so the way it works, as I just said, is you identify stars in the image. That's a very bad process. Then we look for 4-star figures. We actually run at 4 stars, but the code is so beautiful. It's just a switch in the code, and then it all reruns with 5-star figures. I'm very proud of the code. It's absolutely awesome. Then once you've matched this 4-star figure, that implies a pointing of the image and an orientation and a scale for the image, because that's what that quadrangle specifies. And then we ask, how well do we predict the other stars in the image? And this is a foreground-background model. Why a foreground-background model? Because the star identification is bad. There's stars in our image that don't exist in the catalog. There's stars in the catalog that don't exist in our image. And both the catalog and our image have been badly processed. So we don't believe either source of data completely, so we have to have a mixture model of there are stars everywhere that we don't care about, and then there'll be some matching stars. And then we use a utility model to accept or reject. So here's a typical patch of sky. This is just a patch of sky from our catalog, our original catalog data. And the black circles are objects that the catalog generating software generated. And the catalog generating software was not written by us. This is actually, the data that are back here are photographic plates taken by the US Naval Observatory in over the 50 years from 1920 to 1970, or 1925 to 1975. And so this is actually a catalog generated by the US Naval Observatory, not by us. Here's an image coming in. This is a demo from Dustin Lang's thesis. This is an image coming in. This image is truly at this location on the sky, and it found this, it matched that quadrangle of stars. And the way we ensure that there are quadrangles on every patch of sky is we actually very carefully generate a mesh of quadrangles. So the quadrangle catalog we work with is carefully designed so that every patch on the sky has many triangles in it, many quadrangles in it. That's the first one. The second one is no star in the catalog is used in more than a few quadrangles, because some of the stars in the catalog are just wrong. And so if you use them, if all the quadrangles depend on it, you've just ruined your catalog. And we also do this at a range of scales. So we do lots of small quadrangles, medium size. We do it at many scales. So it's a very complicated process, this generation. Now, how do we parameterize and look up a quadrangle? So the key idea is these are geometric hash figures. So we're trying to locate a quadrangle of stars in the database and on the sky. And we're trying to identify the position, the orientation, and the scale, right, of this image. That's our goal. So we need a parameterization of a quadrangle which is independent of position, orientation, and scale. See, we need it to not depend on those things because we don't know those things. Those are the things we don't know, so we need it to be independent of those things. So here's our parameterization. What we do is for the 4 stars, we take the 2 that are most widely separated. We call them A and B. Okay, and then we set up an XY coordinate system such that A and B are on the diagonal. See, and then we look at the locations of stars C and D in that coordinate system. Okay, now this geometric process has many degeneracies. You see, because I could swap A and B and I could swap C and D. So there's degeneracies. That's bad. But it has a very, very nice property, which is that if stars are uniformly distributed on the sky, then the quads parameterized this way are uniformly distributed in 4-dimensional space. So this is an absolutely perfect packing of quads into a 4 cube. So this packs quads into a 4 cube, and then we do a KD tree on the 4 cube, and we look for neighbors. We do neighbor search with a KD tree in the 4 cube. And the reason we have the fastest KD tree in the world is that we never have to do insertions. We just build this tree up front really, really carefully, and and every leaf of the tree has exactly the same amount of data, and we never need to do insertions. So then we can make this beautiful pointerless tree where you can just do everything with just bit operations on memory locations. So this tree has no pointer. That's why we're really fast, because we have no pointers. But we can only do that because we have a very lucky situation. But anyway, this geometric hash was an amusing thing when we figured it out, because it's a very, very clean description of geometric figures. And you can see what the 5-point figures would do and what the 3-point figures would do. Now, one question somebody should ask is, why are you using 4 and not 3, 5, or 6, or 7? Why 4? And thank you for asking that. Excellent question. The reason is, if you work at 3-point, if you work at triangles, there are just not very many triangles. It's a 2-dimensional, triangle's 2-dimensional, right? You do this hash on the triangle, you only get 2 dimensions. And so triangles are not as specific as quadrangles because it's only a 2-dimensional hash. And our uncertainties, remember, the uncertainties in stellar positions live in this space on the sky. So we typically measure these stars with some finite precision. And that means that you have finite resolution with which you can do your search in your database. And at 2 dimensions, that resolution is big enough that you just don't have specificity. So 3 is just not specific enough. So then that says, well, why not use 6-star figures? Because they're really specific. And it's true. If you match a single 6-star figure in an image, you're done. You've basically got it. You've really located every astronomical image in the world with a single 6-star figure. It's really effective. However, remember, our software sucks. And our catalog sucks. So for every star, there's a probability epsilon, and it's not a small epsilon, that star is just crap. Like sometimes the person wrote their name on the image, and the star is the A in their name. Right? And if you have a 6-star figure, you have epsilon to the 6th probability that it's a bad figure. And that just gets bad very fast. Because if there's like a 25% chance that each feature in your image is bad, almost none of your 6-star figures are useful. So it's a trade-off. 4 stars is a trade-off between specificity and usefulness. And reliability, I should say. This geometric hash, by the way, has one other very good property, which is that if I perturb the stars slightly, I get a hash which is very close in the hash space. So this is not a hash in the sense of security hash, which is always trying to randomize the hash relative to the content. This is just doing just the opposite. We're trying to be continuous in the content space. So this is similar to the kinds of hashes that Rob Fergus uses for images, where he wants to be able to move continuously through image space by moving through his hash space. Okay, good. So the performance of this is incredibly high. In fact, this slide was written before our final tests were done. Our final tests gave us 100% success rate on all the imaging from these 2 surveys, each of which produced, STSS produced more than 1 million images, and Galax produced a few tens of thousands in the ultraviolet. The false positives, we get a lot. I didn't bring any false positives. We get false positives in this system. You know, I told you that our customers don't want false positives. All the false positives the system currently delivers are places where there's handwriting in the image. And even that shouldn't affect us. After all, we have a very generative model. That shouldn't affect us. The problem is there's also handwriting on some of the photographic plates that were in the US Naval Observatory collection and got falsely turned into stars. So there's lines of stars where there was handwriting on the plate, and there's lines of stars that we get when somebody submits an image with handwriting on it, and they match. And it's enraging. But anyway, eventually that will be cleaned up. But that's exactly the kind of place where it's a big job to do it, and to do it right, I think, requires some machine learning. That's exactly the kind of thing. In fact, we've already written one paper in which we vastly improved the astrometric catalogs using simple computer vision on the imaging. Oh yeah, so if you want to try it yourself, go to nova.astrometry.net. You can submit images. We get thousands of images submitted each day now. And many of our users are robots, in the sense that there are a lot of robotic telescopes out there that are taking imaging and gathering imaging and doing photometry on the imaging, and a lot of them are our users. We have an API, so a robot can just use us directly. Okay, so here's one thing we did with this. So remember, I started by saying there's all this data in the plate repositories, and a lot of it is in like a manila envelope where they've written the wrong information on it, or the envelopes got swapped by somebody or whatever. So one of the questions we asked is, you know, what we can definitely do. So I should say, astrometry.net is now being used by the Harvard Plate Repository as they scan their plates. They set their coordinate system using astrometry.net. That was one of our goals, and we achieved that goal, so we're working on that. But one of the things that has come up is that when a plate has the wrong coordinates written on it, it also has the wrong date written on it. Because what's happened is the sleeve it was supposed to be in got swapped with some other sleeve. So the coordinates are wrong and the date is wrong. So one question we asked is, can we figure out the dates of the images? Now, how do you figure out when an astronomical image was taken? It's a little challenging. So one thing you might think about is, you might think, well, the stars are in different positions over the night, right? You can see the stars go over like this. The problem is they go over everyone the same way every night. Like, it doesn't matter if you look at the Pleiades over there, if you look at the Pleiades over there, it looks the same. It's just the Pleiades. So that doesn't help. But what does help you is our Milky Way. The stars that you see in these images, what are they? They're burning balls of hydrogen, and they're flying through space. Right? That's what the galaxy is made of. You know, stars orbiting. All the stars are on gravitational orbits around the Milky Way. The sun's on a gravitational orbit around the Milky Way. We orbit the Milky Way about once every, I think, 200 million years. So in 200 million years, in fact, in even just a million years, the constellations around us will look totally different because all the stars are moving with respect to each other. They're all on different orbits. They're all orbiting around the Milky Way. Now, a typical star in one of these plates, photographic plates, moves by a pixel in 100 years. So these motions are not large. They're not big motions. However, there are a lot of stars on the plate. And the stars, we have a good model for those stars. So the question we asked was, can we statistically see when the plate was taken? And what this is you can't read the axes of this, which is good. But anyway, this is a chi-squared measure. This is a measure of the likelihood, the negative log likelihood for the date at which a plate had its photograph, was taken, the date the plate was taken, given time, and the time axis goes from 1900 to 2000. And this is a set of plates that were taken of a particular patch of the sky called the Beehive Cluster, which is an interesting object for this kind of study because the Beehive Cluster contains young stars which have eruptions and novae and stuff. And you'd like to know, if you see a plate where there's an eruption, you'd like to know when did that eruption occur. And so we really do want to know the dates of these plates. Now, most of them do have correct dates. So we were able to use the ones where we have trustworthy dates to test whether we can see it. And you can't read this plot, but on each of those little horizontal bars, there's an X and an O. And the X is the true date, and the O is the date we infer by optimizing this likelihood. So the maximum likelihood dates actually are very, very close to the true dates. And then this is a set of good science quality data. And then this is a set of like crazy data that is corrupted in various ways. And even the corrupted data, we can usually get the right date. Let me show you what I mean by corrupted data. So here's typical data we were running on. So the top three are images that are not corrupted. They're typical astronomical images. And the ones below are corrupted images, corrupted in weird ways. So do you see what corruption has happened here? It's just replication. Why is it replication? You know how you focus a telescope? This is so painful. So nowadays this is very easy, but back in the day, so it's 1972, and you are working the US Naval Observatory telescope, and on the first plate of the night you focus the telescope. The way you focus the telescope is you start an exposure, you integrate for a few seconds, then you close the shutter, you pull the focus of the telescope slightly, you open the shutter, pull the focus of the telescope slightly, nod the telescope slightly, open the shutter, then you close the shutter, pull the focus a little bit, nod the telescope a bit further, open it, and so you get the same star imaged as you pull the focus. And it's a big, fat, ugly thing, and it gets to a very nice little point spread function, and then it gets big and bad again, and that is your focus. And then, but you're not done, because of course, when you're done taking those images, you have to take this plate out of the telescope, you have to go to the dark room, you have to develop it, and then you look at it, and then you know what the focus of your telescope is. I'm not sure that I would have enjoyed astronomy nearly as much back then. But you did get to breathe in a lot of fixer, so maybe that helped. But anyway, I have no idea even what's going on here. I don't know. And this one, you can't see it from this image, but here the telescope is very badly out of focus, and every one of these stars is double peaked. But those three are all you see this one, even this one, with the multiple imaging, you see the date we inferred was only 2 years off the true date for that image. So even when something's multiply exposed, we can still detect it and figure out where the stars are. Okay, good. So that was I'm gonna end with a little bit of philosophy and take questions. So I keep mentioning in this talk that we do not believe the data, and that we don't trust the data provider. And one of the things we need to do is vet the data. And I think this is a really generic issue in all of science. And usually the way we work is we look at the data, look at the fits, and we say, oh, well, these data points probably are wrong somehow, and we cross them out. And we're getting to a point, certainly in astronomy, where that's just not possible. We just released a set of papers on large-scale structure in the universe that had 6 or 7 million galaxies contributing. I mean, nobody can go through and check which of those galaxies are well fit by the model. So we are trying to develop a trust model for data where we trust the data by doing scientific investigations in the data. And that's kind of our thinking about it is that, one of the reasons we have astrometry.net running and one of the reasons we're trying to do science with the astrometry.net outputs is that we would like the astrometry.net system to actually be doing the science itself. We want it to be doing these investigations. So finding the dates of those images is like a science project. So if the system can do that science project and successfully come up with an outcome, that's a very strong argument that the data that went into the system is reliable and useful. And so we're trying to build this kind of trust model for astronomy and for data in general. One of the things we'd like to do with this system that we're very, very far from doing is aggregate the data. We're in an incredible online situation. We have images coming in. Every image, we now know where all the stars were in that image and all the brightnesses of those stars and all the positions of those stars. We should be learning from that information. Right now, we're just returning it to the user. But we should be updating our models. In particular, we can see that a lot of the input data that we're using to calibrate is wrong. So we find that some of the stars the US Naval Observatory has given us are actually not correct stars, or they're in the wrong positions, or they're very variable. We've learned a lot of things about different stars, but we've only learned them in the sense that I know that those problems are there. We haven't learned them in the sense of actually propagating that information back into the system and doing a better job. So one of the things we're thinking about is running a real-time updating sky model that every time an image comes in, the image is calibrated and then updates the model. And then we would have truly an assembly of all the information, all the astronomical information that's ever been taken. So we really have not, actually, when I talk to people, some people think it's absurd that you would have a system that was a model of every astronomical object, every astronomical image ever taken. And other people think it's absurd that we don't have that, because it's actually not that big a problem. There's a billion or so stars with good quality data, maybe 10 billion total in the observation. So you could make a model of the astronomical data with only tens of billions of parameters, which sounds like outrageous, but it's all very sparse. Each image only touches a few hundred or a few thousand stars. So there's a very sparse kind of description of this model. It really is a possible thing to do. The nice thing is that if you were running this, as each image came in, we would be able to report novel information, like, whoa, there's a supernova in that image, or a comet, or there's something anomalous in this image that's deserving of follow-up, and we could even direct new observations. So we really could, in the long run, we could really remove astronomers from the loop entirely, and astronomers could sit by the pool and wait for the SMS to come in that the paper's been submitted. And right now we have various vaporware projects working towards us. They're vaporware in the sense that we don't have results yet, but we are working on trying to build this complete model that runs. I think that I'm getting close to the end. Oh yeah, I wanted to show just one thing that suggests the promise of that. I mentioned, that this is the last thing. I mentioned that a good model of an amateur astronomer is that they only take images of Orion. So if you look on Flickr, I think there's about 10,000 images of Orion on Flickr. So we just gathered them up to look at them, and here's 2 examples. There's one, very nice one. You can't see how nice it is if you saw it here. It's very, very nice. And that one, this one's extremely beautiful, but you can't see it on that. Well, if I turn that around, that won't help either. But anyway, there are many, many beautiful photos. I strongly recommend just type Orion into Flickr and play around. You'll see some amazing things. But one of the things we tried to do was ask, if we take the combined information of all those images of Orion from Flickr and ask, what's the astronomical content of them? So this is this plot is a very strange plot. This is a little patch of the sky, and the red circles are stars that are known in the standard astronomical stellar catalogs. See, we know about a lot of stars, but oddly, it looks like we don't know very much about the stars inside Orion. See how there's a hole in the catalog at Orion? And the big circle is different from the little circles. The big circles are from a very, very carefully made, handmade catalog, and the little circles are from a robot-generated catalog. But these are the state-of-the-art catalogs. Now, the robot-generated catalog deliberately fails here, because in Orion, there's all this nebulosity. So this is nebulosity, so astronomers are worried about running their software in here because their assumptions that it'll be a bright point on a black background fail. So the assumptions of the detection system kind of fail here. But it's nonetheless the case that the professional astronomers do not have a good catalog of stars in this region. Now, what are the blue blobby things? The blue blobby things represent some probabilistic information about where there are stars in the Orion area. And this collection of just random photographs on the web actually give us very strong confidence on a bunch of stars in here. So we could, in principle, have a much better model of this patch of the sky by using Flickr than we have at the present day. So, so there's huge promise if we can automate and work with untrusted data. There's huge promise for astronomical discovery. I'm done.
More questions?
Briefly, I have a question about that picture. So what's the smear? There's an angle.
I know, there's this crazy thing here. So I don't know the answer to that. It is a collection of detected objects. So what we've done is we've run some kind of fairly sensible star detector, and then we're plotting the outputs. We're over-plotting the outputs for many images. Now there's a set of images that are producing things here, and I think one of the things that's going on, and now I'm about to undermine everything I just said, I think that one of the things that's going on is that there's a set of nearly identical images in Flickr that have been labeled a certain way. And we're picking up the labeling, and because they're all nearly identical, the labeling is all hitting at the same place. So I think that's what's going on. Now, so that says 2 things. First is, if we were really going to do this, we actually have to do label detection. And we've known this for a long time. But now, back in 2005, that was very hard. But now there's really good text detectors. You know, there are these things that translate signs on your phone. So actually, we're in much better state for getting rid of labels. The other thing...
These are labels added by astrometry.net?
No, they're not our labels. And the other thing is, the other issue that I brought up there, which is very concerning for projects like this, and we don't actually know how to solve it, people here may know, is that some of the images really are identical. They come from the same source material. You don't want to be multiplying those likelihoods together, right? So there's actually an additional issue, and one of the reasons why we're taking a while to get this done is we want to actually, and I can think of various heuristics we can do, but I would like to think of something better than a heuristic way of identifying that 2 images have the same fundamental source. It's not as simple as just saying, are these 2 images identical? Because one of the main things people do with these data is crop them and rotate them and stretch them and change the colors and all that stuff. So we really do need to understand that problem.
So from the same fundamental source, can you use some kind of identification of the equipment?
Yeah, there's several very key things. One key thing is equipment. Now, one of the problems with equipment, we know a lot about the equipment because when we astrometrically calibrate these images, we learn, of course, that there's distortions. They're not perfect cameras. They have distortions in them, and we learn that there's distortion patterns that are common. And so we can actually classify cameras by their distortion patterns. But the problem is that people take many images with the same camera, and all those images are useful. So but it is valuable when we're trying to understand whether two images have similar provenance. But a related thing is to think about the noise, like the low significance bits in the image. The low significance bits in the image are dominated by shot noise in the photon field, and we were wondering whether or not we can use signatures of that to make signatures for the individual images, like a photon signature. But we're far from that.